So it picks up pieces using his claw, like so. And then there's the fire and forget that I was talking about. I only pressed the button and it knew to raise to that height, handling it with the PID, which I love. And then using the guide system Amanda talked about, if for whatever reason I feel like driving in on it at an angle, it will correct and line me up over the goal properly.
Can you replace it with beer bottles? Or
Should we do it? Next year's competition.
I don't think their parents would have appreciated that comment. Sorry, but
I'm sure my father would like it.
I'm a marketing guy. What can I tell you?
Well, Jacob doesn't know that in the summer it is going to have a little barbecue skew and a beer bottle.
Yes, more for me to program. So another cool feature that we have that is extremely unique to our team, we call it the slip and slide. Something that we found is that these pieces stack into each other very nicely. In fact, that's the way they were meant to be held, so that's why the balls sit perfectly on the barrel. So we took advantage of that to hold multiple pieces in our claw. That's why the claw itself is so high with only 2 pieces in it.
Now all of that action is autonomous.
Yes, exactly. I only pressed possibly, I think, 2 buttons there. So not a lot of work on my part. Now that you guys can see the sensors, some of the simpler ones are encoders, nice and big, how we love them. We have integrated encoders. Unfortunately, they're hidden underneath the robot right now in other motors, but they actually come probably only about that big and attached to our motors here. We have potentiometers. You can see one on the front. Right here we have buttons, really simple, but they help a lot when we were doing our autonomous skills programs. And hidden in the bottom again, these were a big help to us, and we added them just before the Worlds, is a gyro sensor and an accelerometer. We use those again in the programming. The gyro helped us a bunch in getting our bearings, and what we also developed with that is what we called it a yaw follow. Everywhere you go to where there is robotics competitions, you're going to hear something thrown around called a line follow, which is a robot that can use a light sensor to follow along a line anywhere. Well, the problem with that is on these big fields with big robots, we got lines probably only about that big, and they limit us because they don't have them everywhere that we would like them. So instead what we can do now is using this, we don't follow a line, we follow a bearing. So for example, if I were to start the robot here, it sets this to be 0.0, and it rotates all the way around to 360 and then loops back to 0. So with that, what I can say is follow your 0 bearing, and it'll follow a straight line along that bearing this way. Should the robot veer off of it, the bearing will change, and it'll start reading 1, 2, 3, 4, 5, and then start correcting. It'll jump back to that 0 bearing, because that's where it wants to stay. With the accelerometer, we use that for fail-safe coding. Sometimes, should the robot go insane, it doesn't like listening to me sometimes, so it drives past where I think it will. And what would happen then is we'd start hitting walls, we'd bump the claw and bend it off a little bit, or we'd burn out motors, which is no good because that's a lot more work on the build side to repair, and we waste a whole bunch of time. So what the accelerometer does is every time we make any sort of movement with the drivetrain within our autonomous coding, the accelerometer is watching constantly. And if it sees a spike in there, it knows that we have hit something, a negative spike. If it sees a positive spike, we're accelerating to a point. If it sees a negative large enough, it means that we must have hit something. And in that case, it cuts off the robot from driving immediately and stops the code in that position, because we do not want the robot to break on anything. And if you guys did not get to see the bottom, there it is.
Watch the screen.
There we go. The blue things in there are battery packs. You may also be able to see the gyro and yaw. They are hidden by a bunch of wires. As well, you get another look at our tubing in here and some of our wires all wrapped up nicely. It actually expands out down here and underneath the robot where they cannot get caught on other robots or pieces, because that was a huge issue. We got caught on a bunch of other robots because they had their wires all over the place, sticking out of every part of the robot they could. Mechanical-wise, a couple things to highlight would be worm gear in here. People really liked our use of that, and it was a big issue this year when designing claws. The issue with that is to get a claw to close around these pieces, they are actually very smooth and they can slip out. So for one, you need power to grip onto them. If you use a motor to grip it just on its own using gears, that's fine. But as soon as you say, okay, you gripped it, you can stop driving the motor now, the claw bounced back out. And no matter what you did, that will happen. So what we did is we used the worm gear, which means when we drive it in, unless that worm gear is turning due to the motor, it can't bounce back. The gears don't have the play to because the worm gear is that strong. As well, it gave us a bunch more power on squeezing. So it wasn't like we were going to destroy any motors doing that anymore. We didn't have to drive it as hard.